You're listening to the Business Draw podcast. I'm your host Deepak. We are delighted to welcome Dr. Sriram Sankaranarayanan, Assistant Professor in the area of Operations Management at the Indian School of Business, as our esteemed guest on today's podcast. Dr. Sriram obtained his BTech degree from the Indian Institute of Technology, Kharagpur, followed by a PhD from Johns Hopkins University under the supervision of Dr. Soleh Siddiqui and Professor Amitabh Basu. He subsequently pursued a postdoctoral fellowship at Polytechnic Montreal, working with Professor Andrea Lodi under the Canada Excellence Research Chair in Data Science for Real-Time Decision Making. From 2020 to 2025, he served as an assistant professor at the Indian Institute of Management, Ahmedabad. In this episode, Dr. Sriram Sankaranarayanan explores his fascinating work, the cut and play algorithm, computing Nash Equilibria via outer approximations. Let's not keep you waiting. Please join me in welcoming Dr. Sriram Sankaranarayanan to the podcast. Dr. Sriram, thank you for graciously accepting our invitation. It's an honor and privilege to have you with us today.
Yes, thank you for the invitation. It's also a great pleasure for me to join you in this podcast, and I'm happy to talk about the work and anything else that might be of interest to your viewers and listeners.
Thank you. Dr. Sriram, at the heart of your paper is the cut and play algorithm. How would you explain its core idea to someone familiar with optimization but not with the game theory?
Yes, sure. So let me try to first tell what optimization versus what game theory is. So optimization, many people might be familiar with. It is a science of making decisions. You build models and then you have various constraints under which you want to make decisions, and then you have some objective. Maybe if you're a firm, maybe profit. If you're a country, maybe some GDP or other development related indices, etc. But with this objective, you make a decision so that this objective is maximized as much as possible. Now, an extension of this or a generalization of this is what is called as a game. As opposed to optimization, where you are the only one making decisions, in games, what happens is there are multiple parties who are all making decisions. Right? I am going to make a decision in a way that is helping me the most, while you are going to make a decision that is going to help you the most. And the important part is your decisions are going to affect me and my decisions are going to affect you. Right? If, for example, imagine two firms, if I am selling my product and then I decide to give discount in order to expand my sales, you can easily imagine this is going to have an impact on the sales of your product. The fact that your competitor has given a discount has an impact on the sales of your product. Right? So these kind of interactions where there are multiple decision-making parties and they are not coherently making decision. Each decision maker has their own objective and they are trying to maximize their objective and then making decisions. You call this situation, this kind of interaction, game. And the study of this is game theory. So in optimization problems, we try to identify what is called as an optimal solution, which is like the best decision one can make, right? Whereas in games, the standard notion is what is called as an equilibrium, which means, we are all making decisions and we are at a certain place where none of us have any real incentive to choose and make a different decision, right? We are already doing the best we can. There is no way for me to do better than what I am doing, given that the rest of the other decision makers continue to do what they are doing now. This is called as game. So in the heart of this problem, what are we trying to do? We are trying to create an algorithm that if you specify me a game, I would tell you where is an equilibrium of this game, where is a Nash equilibrium of this game, to be more exact. And now the question is, why do you want to identify equilibrium? Why do you want to know what is the Nash equilibrium in a game? That is because these kind of equilibrium concepts have a very large predictive power, right? When firms are competing or when countries are competing with each other, yeah, or any kind of multiple decision makers who are selfish in their objectives, when they are in a competing situation, these equilibria predict what is going to happen eventually. Yeah. So, and we want to understand where are things going to eventually settle down. This is something which we want to know. And computing equilibria helps you achieve exactly this. That's the core heart of the problem that we are considering in this paper.
Professor, you mentioned that non-convexities in games such as integer or bi-level structures made computing equilibria extremely difficult. What was the key conceptual leap that allowed you to address these challenges through outer approximations?
Okay. So, so now we are talking about computing equilibrium, right? So we are given a game and then you want to figure out where is the equilibrium for this game. So whenever you are computing, be it optimization people or game theorists, there is a technical condition called as convexity. Uh, it might be too technical for a podcast if I want to explain what convexity is, but it is a technical assumption. And if that technical assumption is satisfied, then computation typically tends to become much easier. And this is observed in optimization also, this is observed in games also. But the thing is, you are making an assumption. Convexity is an assumption. There are many real life situations where this assumption of convexity is invalid. Okay, so you make this assumption, it's an easy problem, but the downside is you make this assumption, you are not capturing what is happening in reality, right? So now once this assumption has gone away, then there is a question of how are you going to solve optimization problems and how are you going to solve for games. So one of the results in this paper is, in even some very mild ways, if this assumption of convexity is relaxed, yeah, then identifying equilibrium, it becomes a really, really difficult problem. Yeah, the what I said in plain English, this is very formally characterizable. In computer science language, people call it sigma 2p hardness. So that is a formal way of measuring how difficult is this problem to solve by computers. Okay, so this becomes an extremely difficult problem if you want to find equilibrium. But the thing is, if it is difficult problem, it's not that we give up. What does difficult means? It means you require more computational power. You need more time to solve the problem. That's what this notion of difficulty means, right? So optimization, for example, whenever people talk about integer programming, that is a difficult problem. It is a different class. People call it NP-complete. So those problems are now routinely solved by industries. Why? Because you have, compared to say 1990s or 1980s, you have much better computers, much better software. So all this made solving these problems, more possible within the realm of possibility for companies and decision makers. So our key idea here in this paper is the following. So given that there are non-convexities in games, not optimization problem, now in games itself, and that we have these existing solvers which are built for optimization problems that are extremely good for optimization problem, can we use them in some smart way to compute equilibrium for these games? So to do this, what is the key idea? So we make a bridge between convex games and non-convex games, right? So which means our interest is in solving these non-convex games where this technical assumption do not hold. But then we say, okay, you give me your favorite non-convex game, then there is some other game which is living in this convex world, which is the good world, which is easy for us, computationally tractable for it. You can think of it like a friend game. Okay, it's like a friend of this original game. And this friend is something with whom you can do computations really, really fast. Okay, you can write very nice code. You can handle them and deal with this friend game, which is the convexified version of the game. You can compute equilibrium for them really fast. But the question remains, okay, you have now computed equilibrium for a different game. Does it have any repercussions for the original game? So this is a theorem, this is a central result in the paper, is the theorem where we prove that as soon as you get some results for this friend game, which is this convexified version of the game, that translates into something really, really concrete for the original, much tougher to crack this non-convex game. Yeah. So basically, you solve an easier version of the problem, and then you are saying, okay, just because you solve this easier version of the problem, it's not that everything is lost. You can get very valuable insights for the original difficult version of the problem. Yeah, and it is this bridge between convexity and non-convexity is the primary conceptual leap in the paper.
Dr. Sriram, how does the cut and play framework differ from classical equilibrium computation methods such as Lemke-Howson and variational inequality formulations?
Sure. So these Lemke-Hausen and variational inequality, they are used in two different contexts. So what happens in Lemke-Hausen? So when the number of choices each person has, it is enumerably finite. It is a small finite number which you can enumerate and say A or B or C. Then Lemke-Hausen is good enough, right? And if your situation is something that can be written like, okay, should I sell product A or product B or product C? This is all the choice that you have. Then you do not have much use for our cut and play algorithm. I will encourage you to use Lemke-Hausen. Okay, variational inequality, that is a reformulation which works only for original convexity assumption holds, right? So again, when you have non-convexity, variational inequality-based reformulations do not work. So now let me give you, so where is it not finite, not convex? Imagine, for example, airlines, okay? Let's say you are a large airline company and you want to design a schedule for some 100 flights which you fly within India. Okay, now you have a competitor airline company. They will also schedule their flights between different parts of India. Now, how many people want to come to your flights? How many people want to pay for your flights? This depends not only on your schedule, but also on your competitor schedule. Okay. Now, what choices of schedules do you have? And what choices of schedules does your competitor have? Do you have one, two, three alternatives? No, you have numerous alternatives. Correct? You have hundreds of alternatives. Which is it between Delhi and Mumbai? Is it Mumbai between Coimbatore and Chandigarh? Which pair of cities? How many flights? At what times are you going to run this? You have a large, humongous number of choices. Correct? So Lemke-Hausen doesn't work because it's not a small finite number. Variational inequality is also not going to work because in this situation, for example, this kind of scheduling situation, your assumptions of convexities do not hold. They break down in a very catastrophic manner. Yeah, those assumptions are very strongly violated, which means you want something new that can identify equilibria in such situations. And cut and play algorithm, it precisely addresses problems of this type. Yes.
Professor, the algorithm iteratively uses cutting planes and techniques often associated with mixed integer optimization.
Yes.
How does this concept evolve to fit the game theoretic settings?
Yes. So in fact, I would actually go one step back and say they did not evolve too much to cater the game theoretic setting. I will tell you why. Cutting planes has been studied in mixed integer optimization community for multiple decades now, and there is a very, very rich literature, very rich theory, and lot of practical insights that people have developed over time, and they are extremely useful and extremely powerful tools. Right? Now, since these are already, people already have researched and found out what works very well versus what works okay and what does not work, we do not want to reinvent the wheel. Right? We want to basically import all this technology which is already available in the world of mixed integer optimization rather than starting and solving each of these from scratch. Yeah. So we are proposing a few cuts. Why do we propose these few cuts? Because unless you add these elements, the algorithm just breaks down. It does not work. That is what is required to build. I told you, there is a bridge between convexity and to build those bridge, some basic cuts, which we are calling the paper as value cuts. Those are needed. But that aside, it's not a cutting plane research. What we are saying is you have excellent mixed integer optimization solvers. Use those solvers. Do not build things from scratch. Use those solvers. Make only these kind of adjustments which we are suggesting you to do, and that is the detail that is present in the paper. Yeah, so we are not fundamentally creating too many cutting planes rather than using the existing technology.
Professor, the paper introduced the idea of computational convexifiability. Why is this properly crucial for convergence, and how does it reflect the practical limitations of real-world optimization solvers?
Okay, so we have relaxed the assumption of convexity. Correct. That's what I started by saying, and then we say, okay, there is this huge ocean of non-convex problems, right? But if you say just non-convex, I do not say anything more, then they're non-convex sets. They could be really complicated set, which are extremely theoretical, which have, I mean, you can come up with a very mathematical textbook example, a very bad corner case where things do not work. But which means we have to be precise in what we are saying, right? So computational convexifiability is an assumption which we have in our paper, right? So we say we don't need convexity. What you need is something called computational convexifiability. That is a lesser assumption than direct convexity. And what this means is, it means we know of an efficient procedure that, over multiple rounds of what are called as branching and cutting, which are very traditional operations used in when solving non-convex problems. You could do these kind of operations and eventually be able to find the friend. I told we will be finding a friend game, which is kind of a well-behaved game, something which you can compute fast. Basically, we are saying if you have an original game, it is not very difficult to find that friend game. You can find it reasonably fast. Yeah, you will be able to find it. That is the assumption of computational convexifiability. Now, the second question which you asked us, are we making is this a strong assumption now? Okay, because our problem was convexity is a strong assumption, but we have replaced it with another assumption. Is this a strong assumption or a weak assumption? So what we are saying is it's an extremely weak assumption. In fact, many type of problems, all these airline companies. For example, I told you about this scheduling problem, correct? Airline scheduling problem, this kind of problems, and many problems which are typically solved by this mixed integer linear optimization. These are all computationally convexifiable problems. Okay, so there is a huge class of problems that are not convex, but are computationally convexifiable. Okay, so which means the algorithm that we are proposing is going to be applicable and be useful for a large variety of problem formulations. For a large variety of problem formulations, our method will be valid. In fact, I can go one step ahead and say, so far in our discussions, we have not been able to think of a real life example where computational convexifiability does not hold. We have examples of some textbook problems using X, Y, and Z. We have examples of problems where it is not computationally convexifiable, but we cannot think of any real life problem where computational convexifiability does not hold. But convexity does not hold, we can think of lots and lots of problems. There are lots of problems where convexity does not hold. Yeah. So that is how this computational convexifiability comes into picture, and that is needed so that you can eventually find this friend game, which is kind of the well-behaved convex game. Yeah.
Professor, you tested cut and play on integer programming games and Nash
Yes.
games among Stackelberg players. Which of these benchmark classes provided the most surprising insights or challenges?
Yes. So both these linear integer programming games as well as NASP, which is Nash among Stackelberg players, both these fall under the family of computationally convexifiable games. So these are games that we can handle reasonably well. So in the context of integer programming games, things were not very surprising. We did as good as many existing algorithms, and then in some cases in fact in most cases we bet existing algorithms that were more custom made for linear integer programming games. But the situation was different in the context of Nash games among Stackelberg players. So there what happened was almost the same group of people who wrote this paper, we had a previous paper where it was a custom-made algorithm that will work only for NASPs. So we still were not able to beat the custom-made algorithm that was made for NASPs, but still we were able to get concordant results. We were able to replicate the same results that we were obtaining using the dedicated NASPs algorithm.
Professor, in your computational experiments, the algorithm seems to outperform game-specific solvers.
Yes.
Could you share an example where cut and play found an equilibrium that existing algorithms missed or struggled to prove non-existence?
So there are Yes. So in our test set in the in our test set in our paper itself, we have instances of multiple problems where the existing algorithms failed. So they'll tell you the reason that it is failed because the feasible set is what is called as unbounded. Unbounded means it is kind of going to infinities in some specific ways. You do not say, okay, this is the maximum, right? And the existing algorithms, whenever their correctness was proven, they made an assumption that this unboundedness is not a problem, right? Everything is, you have a ball and everything is within that limit. Nothing can grow in an unbounded manner, right? So in those problems, with even giving 10 times as much time as our cut and play algorithm was given, it probably got stuck in an infinite loop or something, but we did not get equilibrium. We were not able to find any Nash equilibrium, or the algorithm did not terminate also. Whereas our algorithm, there were instances where it either found an Nash equilibrium and terminated, or it gave a certificate, it gave a proof that, okay, no Nash equilibrium exists for such games. So we had computational instances in our test bed of problems itself where these kind of situations happen.
Professor, Nash equilibria often represent stable outcomes but may not always be socially optimal.
Yes.
Do you see potential extensions of cut and play that could incorporate regulatory or welfare-oriented perspectives in equilibrium computation?
Yes, absolutely. Yes, you are absolutely right. Nash equilibrium could be very bad, and then even worse problem is there could be multiple Nash equilibrium for a game, and among the multiple Nash equilibrium, one could be excellent, one could be okay-ish, one could be very bad. Correct? And right now, the way our paper, it will return a Nash equilibrium. Right? You cannot control a priori whether you will get the good one, the medium one, or the bad one. You might not be able to control right now. So trying and doing this kind of refinement of equilibria, that is one thing which is a very natural extension one can ask about. Yeah, it's a natural follow-up one can ask about, and we are thinking about this in one part of the research. But the more interesting question is, can you find other forms of equilibrium? For example, correlated equilibrium, right? As opposed to Nash equilibrium, it's a much larger set. You can find much nicer correlated equilibria in a situation where if you are able to mediate between these competing parties. Yeah, if you can act as a mediator, then correlated equilibrium could be a very nice solution concept. Now, as of this moment, if you ask me, for these kind of non-convex games, can you find a correlated equilibrium? If you ask me, I'll say I don't know of any way to calculate them, right? But it is in fact, we in the paper or its appendix already mentions this as one of the key future work and questions that we want to address, because as you rightly said, Nash equilibria could be bad, and in many cases, and it could suffer from a lot of fairness issues. Right, a Nash equilibrium could turn out to be unfair in certain very quantifiable manner. Right, so a natural question is, how can you identify equilibria with nicer properties, other notions of equilibria? That question remains, and at this moment, it is an open question.
Professor, I'd like to conclude this episode with one last question.
Yes.
Looking forward, how might this algorithm contribute to market design AI, multi-agent systems, or policy modeling, where non-convex strategic interactions are increasingly common?
So, AI multi-agent systems, I have not thought too much about that. So I will not speak about that. But let me talk about policy modeling. So NASPs, one of the problems which we talked about. So in fact, I'm working on something like that. Imagine two countries, okay? Let's say country A and country B, and they are interacting with each other. How are these countries interacting with each other? Maybe they are imposing tariffs on each other's products. On different industries, there are tariffs. Okay. Now, country A has its own domestic industries, and country B has its own domestic industries. Right? Now, country A is interested in the welfare of its domestic industries, plus some other terms in the objective also. And country B is interested in the welfare on country B's domestic industries and other similar parameters. And you have trade happening between these industries in country A and country B after paying some tariffs that might be imposed by the government. Now, if you think about it, it is a game. Yeah, you can easily see it's a game because the governments have an objective. They have to meet certain budget requirements or certain whatever policy requirements, etc. Each of these industries also have a profit maximization objective, right? And these objectives are misaligned. What might be good for one country or one industry might be bad for another country or another industry. And if you write a very natural model for this problem, the model is a very non-convex model. And what do you want to find? You want to identify equilibrium, which means where is this game eventually going to settle in? All right. Now, if you want to find an equilibrium, what do you have to do? You want to fundamentally solve a non-convex game and identify equilibria for this game. And here, the previous question that you asked becomes even more relevant. Yeah, they are likely to be multiple equilibria. What is going to be a good equilibria? What's going to be a medium equilibria? What's going to be a bad equilibria? And are there interventions? Are there policy recommendations that could be made so that eventually it is settling at a good equilibria as opposed to a bad equilibria, right? So these are all the type of questions which can be addressed partly by the algorithm presented in this paper, along with some of the algorithms presented in our own previous paper where we talked about NASPs. So these are the kind of non-convex strategic interactions that our algorithm can model with.
Listeners, as we wrap up today's episode, I want to extend our heartfelt thanks to Dr. Sriram Sankaranarayanan for sharing his insights and taking us through the intricacies of the cut and play algorithm and its applications in computing Nash equilibria. Professor, your work truly sheds light on the exciting front fires on operations management and decision making, and we are grateful for the clarity and depth you brought to our discussion. To our listeners, we hope this conversation inspired new ideas, curiosity, and a deeper appreciation for the power of algorithms in shaping real-world decisions. Dr. Sriram, it's been an absolute privilege to have you on the podcast. Thank you once again for your time, expertise, and engaging discussion. Thank you so much.
Thank you. The pleasure is mine. I enjoyed the conversation with you, and thank you for hosting me here.
Thank you.